Very much. Thank you guys for joining in. I'm thankful to the collaborators for letting me talk a little bit about my work on R process enrichment and binary neutron stars. Um, I'm gonna go over a brief overview and then talk about the current existing data that challenges the currently accepted paradigm. And we'll talk a little bit about the future gravitational wave detectors and how they can improve our understanding of the role of binary neutron stars in our process enrichment. So I start with a brief overview of the subject. So what are our process elements? So if you look at the periodic table, basically all the elements, so the hydrogen and helium are mainly produced in the Big Bang. And the elements after that, all the way past the iron peak, are born and made in the stellar factories and ejected into the interstellar medium. Past a mass number of around 70, you will see in this plot that there are two lines. One is indicated by yellow, one is indicated with blue. And these are two different proposed processes that contribute to the formation of these massive elements. The one in blue is called the slow process or S process, and the one in yellow is called R or rapid process. So as you can see, these processes overlap. So an element in that part of the mass number range, an element has a contribution from both processes with different ratios. For example, barium is considered to be mainly an S process element, and for example, an element like gold is mainly an R process element. So, but how are they actually produced, and where are these terms coming from? Our process is a process in which you have a seed nuclei, and this nuclei is being bombarded with a heavy flux of neutrons. So you bombard this seed with neutrons, and there's a series of neutron captures happening, inflating the seed. And then with a lower rate, there is a beta decay happening in the nucleus and turning one neutron to a proton. But the rate of neutron capture far exceeds the rate of beta decay. And this process happens far away from the stability value that that elements are going to become stable. So this process happens, and the name rapid comes from the fact that the neutron capture is much faster than beta decay. So now, if they are similar, if the rate of neutron capture is similar to beta decay, it's called a slow process or S process. Now, to have a look at how these elements are basically formed, this is a plot that shows you that again. So if you look at the red line is where the R process is happening, like basically populating that section of elements, and these elements will later on all decay back to a more stable nuclei. But you can see that there is also this zigzag blue line, dashed blue line, which is the so-called S process. So this happens much closer to the stable value. But as you can see, like an element can be only an R process, it can be only an S process, or it can be a combination of two. It has contribution from both processes. Now, the question is, what are the sources of these R process elements? And the few sources that have been suggested in the literature are neutron star mergers, core collapse supernovae, neutron star black hole mergers, and collapsars. Collapsars are massive rotating stars that happens towards the end of their life. And in this talk, I'm only going to talk about the neutron star mergers and their role in our process enrichment of the universe. I started a beautiful simulation by David Radice, where there are two neutron stars merging. The color coding is basically shows that if it is a blue, it is very neutron-rich material. And as and the color becomes redder and redder, it becomes less and less neutron-rich. So what you should see in this movie is that there is the blue and red components are, so the blue is more ejected in a planar fashion, and the red is more polar, directed towards more polar coordinates. So, and this picture is accepted, but it has a lot of, it depends on a lot of assumptions. For example, what do you consider for the mass ratio of these two neutron stars? How do you treat the neutrinos? And lots of other uncertain physics that goes into these simulations. But people in the community more or less agree that this is what different simulations get, and all agree in the, broadly speaking, the geometry of the ejecta and the distribution in neutron richness. The neutron stars, they have very high yield of R process elements, and the only thing that that really limits and is challenging to accept them as the main source of R process in the universe is that they're very, very rare. So per 1,000 core collapse supernovae, you have one neutron star merger. But on the other hand, their yield in our process is 1,000 times larger than core collapse supernovae. So what is the main size of our process enrichment in the universe? The way people try to distinguish between the sites, one classical way is to basically study the rates and yield. And so if you have a rate, if you know the rate of a process, and you know the yield of the process, you predict by multiplying this through a constant mass project that this process has generated over the course of universe cosmic time. So there are lines of constant mass you can draw, and if you know your process rate or yield, then if you know the mass that is present in the Milky Way, for example, then you predict a certain yield or rate, depending on which one you know better. And you go and check whether your theory can work out and with these numbers or not. So people have played these games. This is a recent compilation of the work presented in Rosberg et al. 2017. Well, the x-axis shows the rates of these mergers, and the y-axis shows the yield of the ejecta. So as again, you have a constant mass lines, and overplotted are different expected either yield or rate of a process. So these are games people have played, but the uncertainties are so large that really, at the moment, we cannot say that this approach is going to tell us much about the main R process enrichment size of the universe. So we need better approaches. In the present, we have three main avenues to go after this question. One is the well-studied GW 170817, which has been much talked about in the literature. The actinide booster stars, which I will not talk about, but they're very interesting stars, and the ultra-faint dwarf galaxies. And in this talk, I'm only going to talk about the ultra-faint dwarf galaxies and show that they by themselves also are very powerful to limit and constrain what are the possible sites of our process enrichment in the universe. So what are ultra-faint dwarf galaxies? These are satellites of the Milky Way that are dark matter dominated and very small in size, and also a stellar mass. So their stellar mass is about like less than 10 to the 5 solar mass. And it is believed that their star formation has been seized since redshift 6 or 7. And they're very easy to study because we know that they haven't had like multiple star formations first in their history. They are very like clean, isolated systems that haven't been really polluted with outside star formation. And if you can find one of them to be R process enriched, then it is a very powerful tool because they are very clean systems. The one notable example is Reticulum 2. Reticulum 2 is one of the R process enrichment, which I'm showing you in this figure. Probably you cannot tell where the galaxy, where the Reticulum 2 is, because it is an ultra faint system. And if I overplot the stars that are associated with this galaxy, you will see this red, and then you see all these circles, and they are color coded with their probability of association to Reticulum 2. So if I go back and forth, you can see like this, the job of really identifying, detecting this galaxy is extremely challenging. And they have just been starting to be discovered after 2015 or 16 by Dark Energy Survey. But as I said, this Reticulum 2 is an interesting system in that it has been observed to be R process enriched. So in this plot, I want you to just look at the middle panel, where the x-axis is the metallicity and y-axis is europium over H. And you can see that there are 7 red circles that show the 7 stars of these ultra-faint dwarf system has been detected to be europium enriched in their spectra. They have 2 stars which are showing with downward arrows, which are upper limits. But the other colored points in this plot shows all upper limits, and these belong to other ultra-faint dwarf systems in the galaxy. So we have upper limits for the rest of the system, and there's only this galaxy, and recently there's a Tucana 3 that has been also observed to be R process enriched. So these are very rare systems, and we want to understand how come they became R process enriched. So the issue with these systems is that they are very, very small systems. And the question of whether a neutron star merger could enrich them with R process is hard because of 2 facts associated with neutron stars. Neutron star binaries, when they are formed, come with 2 properties. One is that they have a large natal kicks of order of 100 kilometers per second or more. And the other is that when the neutron star binary is formed, it takes a long time for it to lose, to shrink due to the orbital separation of the 2 neutron stars to shrink due to emission of gravitational waves. And this is on the order of 1 to 10 gigayear. Well, if you just say x is equal to v times t, and you multiply these 2 numbers, and you will see that the neutron star really, the neutron star binary, when it merges, is far outside the virial radius of these small satellites. So there is going to be an R process enrichment, but it's going to happen in the intergalactic medium. How did it enrich the ultra-faint dwarf system? So we went on and we analyzed a set of population synthesis models, and we went in and said, okay, we want systems or binary neutron stars that satisfy the criteria that they don't travel far from their birthplace before merging. And this is a simple T times V cut. And you find such systems. We have performed here, for example, the x-axis is the center of mass velocity of the binary, and the y-axis is the merging time scales in log and in units of millions of years. There are, you can find such systems, and when you analyze, so the red shows the population that satisfies this criteria, and when you go and analyze, you will see that these systems are very unique, and you have to actually put them by hand. There is a specific process that makes them, and whether this process exists in the nature or not, we don't know. So The process that makes them is a peculiar process called a case VB unstable mass transfer. And regarding, I mean, forget about the name. All that it means is that during the process of the formation of the binary, there are two specific processes happening back to back. They're called common envelope process. And that is when a neutron star rips off the envelope of the donor in hydrogen, then subsequently also rips off the envelope, the helium envelope of the secondary. So during the special thing about this process is that normally only one common envelope phase happens. There is a hydrogen envelope with a strip, the first rectangle, and then there is a core collapse supernovae, and then the two neutron stars wait to merge. But if there is a second common envelope process, then you really bring two neutron stars very close to each other, so that the merging time is very, very small, and that helps you to merge fast before you travel way outside the virial radius of your host. Whether this process exists in nature is debated. There is no consensus, and the ultra faint dwarfs, if you want to enrich them with binary neutron stars, they need something of this small. They need something similar to this. They need something that's called the fast merging channel. We have simulated this fast merging channel in ultra faint dwarf galaxies. We did a Zoom cosmological simulation on ultra faint dwarfs, and you can see that if you impose a fast merging channel into the system, your simulated stars that I'm showing in green agrees. These stars agree in distribution compared to the 7 stars of the reticulum 2. And this I'm showing in the left panel. On the right panel, I'm showing the gas distribution in metals, which are shown with black contours, and europium, which are shown in red. As you can see, these contours are basically co-centered, so they come from the same region in the galaxy. However, if by chance, if your neutron star binary takes place off-centered, so this is a case that happened randomly in one set of our simulation. If the neutron star binary takes place far from your star forming region and then it expands and dilutes, as I'm showing you the gas phase in these plots, then of course the level of the enrichment of your stars drop. So this is very sensitive to where the neutron star binary merges, and we definitely need a fast merging channel. So now this is ultra faint dwarfs, and also you can ask the same question for the R process enriched stars in the Milky Way, and we did a cosmological Zoom simulation of a Milky Way type halo. Clockwise from top left, I'm showing you dark matter, hydrogen, R process, and metals. So R process in the lower right, metals are in the lower left. Panels, and this is a cosmological simulation where core collapse supernovae produce the iron, and binary neutron stars produce the R process. You will see towards the end of the simulation that these neutron star binaries that are produced, they receive natal kicks, and they also come with long delay time distribution, long delay times. So therefore, towards the you will see that these neutron star binaries will travel far from their birthplace and then explode in intergalactic media. Do you guys see the simulation? I'm seeing it freeze out.
Yeah, I'm also not seeing anything running.
No? Okay. Let's see. Let me see if,
Is it
let's hope
running on your
for,
computer?
Now
yeah,
I see it. Yes.
Oh, now it moves, yeah.
but it froze midway. I'm not sure. I mean, I give it another shot, but maybe, maybe it will fail. We'll see. But all I want to say that at the end of the day, you will see that there are blue sites with no corresponding red, and then the reds no corresponding blue. So okay, it stops in the midway. So unfortunately, you cannot see the simulation all the way to redshift like 8.5. So
Mohammad, does it stop on your computer or
yeah,
it
it just
stops?
stops on my. Yes, yeah.
Ah, so it's a problem in the file or something. Yeah,
Yeah.
it's not with Zoom.
Nope, nope.
Okay.
It is too much pressure on the laptop. I don't know.
Okay. Okay.
So
You maybe. Okay.
um, in any case, when you at the end of the day, you analyze the data in the simulation, you will realize that there is a mismatch between the observed ratio. So what am I showing? So this is a redshift evolution of fraction of what? Fraction of middle four stars that are our processing rate. The observed fraction is shown with black circles, and the lines show the fraction that I get from my simulations. And well, there is an order of magnitude difference between different classes of R process and neutron stars. And the black line is closer to the data compared to the colored line, but the only difference between the black and the colored line is that the delay time is pushed to incorporate more fast merging channels. So we need that process to be active in the early universe. So more investigation needs to be done, and this is a serious problem at the moment with the paradigm of binary neutron stars being the primary site of our process enrichment. So this was one approach. So what are we going to do next? So the future directions come from I believe, three different approaches to this. So first, we need to lay out the science for the third generation gravitational wave detector. We are already learning from LIGO with strange events such as 190425, which is the massive binary neutron star. And there are still puzzles in our process enriched systems such as globular clusters. I will touch upon these topics. I start with third generation gravitational waves. The reason they are important is that the question is, what is the cosmic history of binary neutron star mergers? So cosmic history of binary neutron star mergers, if you want to know that, okay, you start with the cosmic history of star formation in the universe. Then you add a delay time to it because, you know, the neutron star binaries are formed, but it takes time for them to merge. And how long will they merge? What is the distribution? We have no idea. And depending on your delay time, you will get a different distribution of the redshift. So the question is, do we know what it is? Can we map this? The way you parameterize this is that you say, okay, the whole population of neutrons or binaries are born with a probability distribution in merging time scale. It can go as power law distribution to the -1. It can have a shallower slope. It can have a steeper slope, which is pushing systems to have a faster merging channels. Or this another parameter you can play with is the minimum time, like it's the minimum time or the smallest separation that they can be born. And you can change that too. So all these parameters, I mean, this is just two parameters in this the simplest model. We can have these two parameters to play with. And then these together give you this different distribution. So in the black line, I'm showing you what happens if there is no delay. And then if you play with these two parameters, you get all these sorts of different curves and a pretty completely different distribution of merger rate as a function of redshift. Now, the question is, can we tell apart these merger rates and what instruments do we need, what detectors do we need? And can LIGO does it for us? So one way before we get into the gravitational wave detectors is that to look at the host galaxies of the binary neutron star mergers that we're going to detect. For example, LIGO says, I observed a neutron star binary system. People go and watch and find the host galaxy. So why the host galaxy can be informative? So if you look at the Hubble classification, there are dead galaxies and there are early type galaxies and there are late type galaxies. There are blue galaxies. So the blue galaxies on the right and then the red galaxies on the left. These systems, these two types of galaxies, generically have different star formation histories. So the different star formation histories of these systems is such that the more massive systems, the red ones, have their star formation already way in the past and has been for a long time they have been quiescent. Unlike the blue galaxies, in which the star formation is more extended, cosmic life and cosmic history. And now, if you observe a system happening in the dead galaxies, you know, in the local universe, if you see that all of the neutron star binaries, mergers, are happening in dead galaxies, you might ask yourself why, and you might say, okay, I know that they are dead since, for example, redshift 3 or 4. Therefore, the delay time should be very long. It should be on this scale of 10 gigayear, such that I see them now happening in the local unit. So depending, and the other way around for the blue galaxies. So if you play this game, we played this and then we arrived at the conclusion that you basically need on the order of 300 detections of a neutron star merger with its host to be able to say, to constrain these two parameter models to within 10%. We have so far only one detection with the host, so probably this is not going to happen anytime soon. So we need other ways. We need to see whether LIGO can tell us, but unfortunately LIGO cannot tell us. LIGO has no power in differentiating between those different delay time distributions, because if you look at this plot, this is the detection rate expected for different models for LIGO. And the thing about this is that this is rescalable. You can always multiply one curve with a constant number and get the other curve. And this is because you cannot probe into the redshift. You cannot really see the derivative of those lines as a function of redshift. And again, that's because LIGO's horizon is so small. You cannot probe to actually see the peak and the drop off these curves and where they happen. So we need feature detectors. They are in this plot, I'm showing you the reach of these feature detectors. On the left side of this circle is for neutron star, and the right is for black holes. Different lines of different colors show you the reach of the gravitational wave detectors. For example, LIGO O2 is shown in O2. Shows that you can maybe reach the neutron stars. You can detect neutron stars a little bit, but more works more for black holes. The same is for A plus, the next upgrade. So A plus really probes into the bulk of black hole mergers, but not much for neutron stars. And the reason is simple. The reason is that the black holes are just more massive systems. It's easier to detect them. So if you go all the way to lines noted by CE1 and CE2, which is a featured gravitational wave detector, you can see that for black holes, you can already observe all the black hole mergers in the entire history of the universe. But you have a harder time to do this for neutron star binaries. So the question is now, if you draw the same plot for future detectors, how is it going to look like? So there are two future detectors. Cosmic Explorer is basically LIGO, but with 40-kilometer arm instead of 4-kilometer. And there is an Einstein telescope, which is a triangle which a length of 10 kilometers each. Underground, this is a proposed detector. So these two are the main detectors have been much discussed in the literature. And if you plot the same thing, for example, for Cosmic Explorer, this is what you get. So this is very different than what we had for LIGO. Now you can differentiate between these curves. And first of all, you can differentiate. And also you can see that the redshift reach for LIGO was 0.1. Now this is around 3 or 4. And for LIGO, it was on the order of 100 on the y-axis, measured rate per year per DZ. Now we're talking about hundreds of thousands. It's completely different scenario. And you might say, oh, that's the end of the story, and we will pin down the measure history of binary neutron stars, but that's not the case. This is, yeah, as I said, this is the LIGOs in comparison. It is even smaller than that. So now, it is not actually easy, even with these telescopes, to map out the measure history of binary neutron stars. And the reason is that there is an inclination distance degeneracy. So if you want to know the redshift of a source, you need to know its luminosity distance, which we show here by dl. And to know it, you have to know both polarizations of gravitation, your gravitational wave. So h of t is your strain as a function of time that your detector just detects, but it's a superposition of the plus polarization and cross polarization of gravitational wave. The f functions are just your sensitivity of your detector to either plus or cross polarization. You can see if you want to know dl, you need to be sensitive to both h plus and h cross to solve for both cosine of the angle on the sky and distance. So it's a two equation to unknown. And current detectors have difficulty of, LIGO is, detectors you build is sensitive to one another, but third generation telescopes are sensitive to both polarizations. Now, you play this game and for black holes, and you discover that the distance uncertainty for low redshift black holes is about on the order of 20%, median 20%. If you have two, for example, like a Cosmic Explorer and Einstein telescope working together. But it really blows up. If you go to higher redshifts, it's going to be 100% uncertainty in distance. And so then, therefore, it is completely useless. Now, if you unfold this for binary neutron stars, then you get a relationship for distance uncertainty based on simulations that goes as the fractional uncertainty grows as redshift. So basically, the redshift uncertainty goes as z squared. So it really blows up easily. And when you fold this in, you will see that it's not that you open up this telescope and you're like, I detected. I know the redshift distribution. It still takes 1 year of a network of these telescopes to observe the sky, and you still get within 10% accuracy of the parameters of your delay time distribution. So it is still very challenging. There is I'm going to switch a little bit to talk about this new event being observed in GW 190425. This is a massive binary neutron star system. This is discovered by LIGO. And the strange thing about this system is that it is massive. We haven't observed such massive systems as a binary neutron star before. And this is 5 sigma away in mass from the bulk of the galactic binary neutron stars that have been observed before. Now, I don't think if anybody knew why all the binary neutron stars were clustering around the total mass of 2.7 or 2.8. But now we have this system. If it is a binary neutron star, then its mass is completely different. And another weird thing about this system is it has a high rate. So if you plot the merger rate as a function of mass for this system, is that I'm showing you the rate for the GW170817, which is the first neutron star binary that's observed, and 190425. They are it's a little bit less, but they are comparable. But the expected rate is actually like 10 times lower. You might say, oh, this is between 2.8 and 3.4 total solar mass, so why should it be 10 times lower? The thing is, if you really want massive neutron stars, the progenitor mass, the progenitor stars that make them have to be like on the massive side. And you fall into the IMF of stars being born according to a certain IMF, you'll see that you expect the number to be 10%. 10% of the rate that you had for 1708 system. So the question is, how come it has such a high rate, and how come we missed them? And we speculate about this in a recent paper we submitted in our archive, and we say, hold on a second. All the binary neutron stars you have observed are discovered in radio searches, and find a pulsar around another neutron star. And if you look at this plot, this is showing you period of a neutron star and its period derivative on the x-axis and period derivative on the y-axis. So if you know the period and you know the magnetic field, you know the period derivative. So you can see the lines of constant magnetic fields and decay times, and they're cutting them as you in this panel. What is being shown is that there is a blob of pulsars, and then there is millisecond pulsars down left, and there is a line called death line, which is that if you are a neutron star, if you're a system in that parameter space of magnetic field strength and period, then you're going to be missed. And pulsar searches in radio sky is not going to find you in the sky. So this is called a graveyard. It's the term for that region parameter space. So we proposed and we suggested, is it possible that basically GW190425 is a system merging in the graveyard? And if that is the case, we have to come up with a mechanism in which you bury the magnetic field of a neutron star through a mechanism that we're thinking about, such that mechanism also increases the mass of the neutron stars. So you have a mechanism, maybe it's a failed supernovae, we don't know, that originally makes a GW170817 system, but there is mass falling back onto the system, increasing its mass, and also burying its magnetic field. Would that be possible? Is that a scenario? We are still thinking about this, but it's very difficult to explain this system otherwise, and the main challenge is the measure rate. The measure rate, although it is one system, we have to see, we have to wait for more data. But if it holds up, if this scenario holds up, and 03 and 04 basically confirm this picture, then we really need to rethink about the assembly of neutron star binaries. And maybe all the things I showed you, these are all need to be revisited and resimulated and rethought. We really, this is a shocking event, and deserves a lot more work to understand. I will just show you one slide for the case for globular clusters. And again, very, very strangely, we see globular clusters with a very narrow range in metallicity and wide dispersion in our process. So here is the list of them. X-axis shows the metallicity, and the y-axis shows the R process, or the europium, which is an element candidate for our process mechanism. over iron. And you can see, for example, for M15, there is a wide range of European gravity for its stars of the M15, and very range in metallicity. And if the source is a neutron star, it's exceedingly difficult to make sense of this distribution because the gas that made the globular cluster needs to be homogeneous. If it is homogeneous in Fe, then you either have to like make it through a second generation of stars, but then that's also very difficult because the neutron star is going to escape because the potential well of the globular cluster is very shallow. Or the gas was inhomogeneous in European, which is also very hard to propose because the scales are so small. So this is also a challenge. So at the moment, I think this and the GW190425 are the two main things that we can work on and have a look at what we can learn from the third generation gravitational wave telescope and whether they even can shed some light on this binary neutron star merger history. I am going to summarize the talk by saying 3 facts that 190425 completely challenges our understanding of binary neutron star assembly. We need third generation gravitational wave telescopes to map the merger history of binary neutron stars. And we don't have much better ways to do this. We are working on a new proposal, new theoretical way to do this, but extremely challenging, again, very challenging way. It is very challenging task to do. And finally, sounds like we need fast merging channels, but the theorists don't agree. Those who are expert on binary stellar evolution, one will tell you that this process exists, one will tell you it doesn't exist. So there is no consensus in the presence of these, but the data shows that we need them, and we need them abundantly. That's the end of my talk. Thank you so much for listening and taking a break from the news. If you have any questions, I'm happy to answer.
So, Mohammad, this is Josh Grindley. Can you hear me?
Yes.
I've got a question and a comment. The question is 1904-25 is not ruled out, as I understand it, as being potentially a black hole neutron star merger. Isn't that?
Yes.
It's consistent with the data. So if it is, then of course that solves the binary neutron star question that you're considering here. But if it is a neutron star, there's no problem with making the millisecond pulsars. We've understood that now for the better part of 20 years. It's in low mass X-ray binaries that they get spun up, and that happens 10 times, almost 100 times more frequently in globular clusters than in the field because of the density. And back in, I think it was 2006, I had a paper with Simon Porteous-Schwarz and Steve McMillan on producing neutron star binaries in globular clusters by exchanging, in an exchange collision, a neutron star, which we know are relatively numerous in globular clusters to produce this whole X-ray binary population, that interact with an existing millisecond pulsar low mass main sequence star companion, and exchange a neutron star for the main sequence companion. So that's a formation mechanism for making something that might produce the 1904 25 event, it would be in a, you know, it would have come from a globular cluster, because you have trouble otherwise invoking.
Sorry, go ahead.
Somebody else is speaking. Anyway, that's the question and the comment. I don't know if you want to comment on either
Yes. The issue of the neutron star black hole, whether it is a neutron star black hole, that would require the black hole to be in a range that's called the lower mass gap. So
yeah, exactly. But there are X-ray binaries that live in that mass gap. That mass gap is not
as strict. Yes, is not as strict as if it is below 5, then you have a. But if the rate is so high, then it really again needs us to rethink about the rate of fallback and how did you, or I mean, the formation rate of these mass gap black holes.
No, I agree. That's a problem. But there are at least 2 of the black hole LMXBs that have masses down in the 4 to 5 solar mass range. They're not all at 8 by any means. So how we made them, or how such low mass, you know, black holes were produced, I agree, is not obvious, but data suggests that they are there.
I see. And I haven't thought about this exchanging globular clusters. This is
that works relatively well, because in the collision cross sections are large, and it's going to happen. The question is whether it would explain this event in the field. That's another question. How you know where the system really is. It's presumably no longer in a globular cluster, although I guess we obviously can't rule that out.
Mm-hmm. Mm-hmm. Yeah. No, that's very interesting. We should talk and think whether this really holds up and really can kill the magnetic field, and such that you always go to the graveyard.
Yeah.
That's very
interesting. As far as killing the magnetic field, that's another very old problem. I don't think anybody really understands what's doing it, but there's no question that this is what's happening. All of those systems that we see as millisecond pulsars are all 10 to the 8 Gauss, you know, fields, and presumably they weren't born that way.
Exactly.
So the usual picture is that the field is buried by accretion, but that's raises its own questions, because these things have been accreting. And the other comment that I was going to make is that, of course, the high mass of this neutron star is also not a problem, because we do see millisecond pulsars with masses up to 2.1 or 2.2. Mm-hmm. So they're not all at 1.4 as they are in the high mass systems.
Yes, although
again, that's because they probably have gained, you know, up to half a solar mass just from accretion over lifetimes of giga years.
Yes. So there's no question that you can make them. You can make one. The question is, how can you make the rates to match like the observed galactic or GW7 There are pathways to make them, for sure. The question is, if they're massive and in a binary system, would the predicted rate of the formation mechanism you propose is going to match or be in the same ballpark of 17? But otherwise, it's whether we can make one massive or make a neutron star in principle that massive. Yes, I agree. Yes, absolutely.
Do we have any more questions?
Hi, Mohammad. This is Anna. I have a question about your simulations, and I guess in general about how the sites where you can study our process element formation. So far, you focused on dwarf galaxies and now mentioned also globular clusters. So I wonder, like, based on your simulation work, does it look like we'll ever be able to study those processes in the galaxies like the Milky Way itself? Or is it always going to be too confused with everything else that's going on?
So mostly the simulations, not my simulation, other group simulations they do R process, they study R process enrichment as a post process. And they tag some particles as binary neutron stars, and they study the distribution and at the end of the simulation. But the simulation that I ran was with that like 5 parsec resolution and the mass of the stars and particles being about 50 solar masses. I could not run the simulation below redshift 8. It generates so many particles, as you can imagine.
Mm-hmm.
Typically, the stellar particle mass in the simulation is 10 to the 4, 10 to the 5 solar mass. This is like 4 order of magnitude, like 2 order of magnitude less. And to study them all the way down to redshift 0, I could not even run it past redshift 7. It's impossible. And you have to do this approximation and post-processing. But then when you do that, then there's so much free parameter. For example, you can say, for example, the mixing, like how well does the ejecta of R process dilutes with the hydrogen presence in the interstellar medium? And depending on your assumption, you can either match the data or not match the data. Mm-hmm. You can always tune your parameter to match. The result I showed you, I don't try to tune anything. I just said this is the output of the simulation, and I trust my mixing due to turbulent mixing because I can resolve it by 5 parsec simulation. But if you don't have it, then really there's no good way to say whether you want to trust or not. You can always rescale. You can always assume a different mixing efficiency and get what you want. And this has been done in the past, and everybody claiming that neutron star binaries answer the question. And of course, you can always make it work, but the absolute numbers, if you really let the simulation for itself decide, has a problem. And I don't know. I think the only way to go forward is to run an ensemble of zoom simulation of ultra-faint dwarf galaxies, and compare it to the statistics of ultra-faint dwarf galaxies in the Milky Way, assuming that you understand the star formation history of ultra-faint dwarfs. Simulating the whole Milky Way with such high resolution, at least I could not possibly even do it after below redshift like 6 or 7. I don't know if I answered the question.
Yeah, you have. I was just thinking if it's possible at all, because of course ultrafaints are great targets because you know that they had their star formation shut off very early on. But there are like so few, right? We have only reticulum 2 and maybe Tucana 3 that have our process. So I was wondering, like, could you is the motivation of maybe having more stars like enough of a motivation to be able to run to the Milky Way itself, but it might be prohibitive at the moment, sounds like.
I would say the best bet is to run a simulation on an ensemble of halos of progenitor halos of ultra-faint dwarfs at high redshift. Like you select, let's say, this halo at redshift 6 is P of probability of this being a progenitor of an ultra-faint dwarf by redshift 0 is like 90% or something. And then you model, like you resimulate them with baryonic physics at high resolution, and then you do a simulation on hundreds of them. And then you see whether 10% of them get our processor enriched or so, and what it takes for them. But I haven't done that. I have only been for like 2 or 3 systems back in like 3 years ago. But for sure, like this would be amazing actually if this collaboration, for example, can do it. That would be amazing.
Cool. Thanks.
Do we have any more questions? No? Okay. If no, then let's thank our speaker. I know, how do we thank us? Do we turn on the microphone, everyone, and clap? I can clap. Anyway. Okay, so thank you, Mohammad. And yeah, I hope we'll meet you soon after the COVID-19 ends.